We all know large language models have a big problem. They can be incredibly confident and incredibly wrong. We call it hallucination, making up facts, figures, you name it. And this isn't just a minor glitch, it's a fundamental barrier to safely deploying these models in high-stakes fields. Today, we're diving into a paper that offers a really clever new approach to catching these AI-generated lies right at the source. Exactly. So in this explainer, we're going to break down the paper When Models Lie, We Learn. We'll kick things off by framing the core challenge of pinpointing these errors. Then we'll introduce the new tool from the paper, PsiloQA. We'll look at how it's built, how it actually performs in experiments, and finally, what its success could mean for the future of AI safety. All right, let's set the stage. The real problem isn't just that models hallucinate. It's that even a single incorrect word or number can completely corrupt the meaning of an otherwise perfect response. This makes the ability to find not just that an answer is wrong, but exactly where the error is, absolutely critical. And that brings us to a really key distinction in this field: sequence level versus span level detection. You can think of sequence level as a blunt instrument. It just flags the entire answer is wrong, even if the error is tiny. Span level detection, on the other hand, is like a surgical tool. It identifies the specific incorrect phrase, the span, which is far more useful, but as you can imagine, a much harder problem to solve. And that difficult problem is precisely what this paper's main contribution is designed to solve. They've introduced a new dataset called PsiloQA. It was built specifically to address the major shortcomings of existing benchmarks, which are often expensive to create, limited to English, and don't provide that fine-grained span-level detail that Alex was just talking about. The goal here was really ambitious: to create a benchmark that's not only large-scale, but also multilingual and cost-effective. And one of the most important aspects is that it uses natural hallucinations. These are genuine mistakes that models make when they don't have the right context, not just artificial errors that a human has manually inserted. That makes the whole benchmark much more realistic. And this table from the paper really drives that point home. Sarah, can you walk us through how PsiloQA stacks up against the competition here? For sure. If you look at datasets like Mushroom or RAGTruthQA, they're valuable, but they have their limits. PsiloQA really stands out because of its sheer scale. We're talking over 60,000 samples, its support for 14 languages, and the fact that the whole thing is generated automatically. That automated process is really the secret sauce here. So how on earth did they do it? How do you create such a massive, high-quality dataset without an army of human annotators? It's a really elegant four-step pipeline. First, they use GPT-4o to read Wikipedia articles and generate question and answer pairs. This establishes the ground truth. In step 2, they take those same questions and give them to other LLMs, but this time without the source text, which induces natural hallucinations. Then, in step 3, GPT-4o comes back in, but this time as a referee, comparing the hallucinated answers to the ground truth and tagging the exact spans that are incorrect. And finally, an automated filter cleans out any noisy or subjective examples. And the result of this pipeline is just staggering efficiency. The entire dataset, all 60,000 plus annotated examples, cost only $535 to generate. Now, compare that to a smaller, human-annotated dataset like RAGTruthQA, which the paper estimates would cost around $3,000. It's a game changer in terms of cost-effectiveness. And it's not just about the cost. The diversity is also really impressive. You can see from this chart that while English makes up the biggest slice, there are thousands of high-quality examples across 13 other languages, from Hindi and Chinese to Finnish and Catalan. That multilingual depth is a huge step forward. Okay, so we have a massive, cost-effective, and multilingual dataset, but here's the billion-dollar question. Does it actually work? Does training a model on this synthetic data lead to a better hallucination detector in the real world? Let's get into the experiments. The results are pretty compelling. This table shows the performance of different detection methods on the PsiloQA test set. While some approaches did okay, it was the fine-tuned encoder models that really dominated. Specifically, a multilingual model called mmBERT was the top performer across nearly all 14 languages. It excelled on both average precision and the more demanding IOU metric, which measures how well the predicted error span overlaps with the actual one. That's fascinating. So the success of mmBERT, which I assume stands for Multilingual BERT, raises a really important question. Did training on all 14 languages at once actually give it a competitive edge compared to models that were only trained on a single language? It absolutely did. This next table demonstrates that quite clearly. The model trained on the full multilingual dataset consistently outperformed models trained on just a single language, even when testing on that same language. This is a fantastic demonstration of positive cross-lingual transfer, where learning from one language actually improves performance in another. All right, that's a clear win for multilingual training, but that brings us to what I think is the most critical experiment in the whole paper. How does a model trained on the synthetic, cheaply produced PsiloQA data fare against one trained on a premium, human-annotated dataset? Well, this is where it gets really interesting. The researchers trained two separate models, one on the English portion of PsiloQA and another on the human-labeled RAGTruthQA dataset. They then tested both models on other, independent benchmarks, and the results were clear. The model trained on the synthetic PsiloQA data was the winner, in some cases by a massive margin, like the 45-point F1 score improvement on the Shroom benchmark. Just let that sink in for a moment. The synthetically generated dataset, which was more than 17 times cheaper to produce, resulted in a hallucination detection model that was not only better, but also generalized more effectively to new data. That is a pretty profound result for the field of AI safety. It really is a major breakthrough. So, to wrap up, let's summarize the key implications of this work and also touch on some of the limitations that the authors themselves rightly point out. So, 4 key takeaways. First, for this specific task of span-level detection, fine-tuned encoder models are currently the right tool for the job. Second, multilingual training isn't just a nice-to-have, it's essential for achieving state-of-the-art performance. Third, and this is the big one, high-quality automated synthetic data can be not just cheaper, but actually more effective than human annotation. And finally, this entire approach provides a scalable roadmap for creating the next generation of AI safety tools. Right, but it's not a silver bullet just yet. The authors are transparent about the limitations. The whole annotation pipeline relies on GPT-4o, which could introduce its own systemic biases. The dataset is also narrowly focused on the task of question answering, and it uses Wikipedia as its sole knowledge source, which might not transfer perfectly to other domains. Still, this work points toward a really powerful paradigm, using our most advanced AI systems to build the tools that make them safer and more reliable. It really leaves you with a final, forward-looking question. What does the future of AI safety look like if we can fully automate the creation of our own evaluation tools? It suggests we could be on a much faster path toward building AI we can genuinely trust.